Okay, let's dive right into this explainer and look under the hood of modern zero-shot text-to-speech synthesis. If you've been marveling at how incredibly realistic AI voices have become lately, seriously, it's kind of spooky, you are definitely in the right place. Today, we're deconstructing a breakthrough system called VALL-E to figure out why treating audio like a foreign language is actually the secret to its success. You know, humanity has been on this centuries-long quest to build a talking machine. Just look at this. Wolfgang von Kempelen's speaking machine from way back in 1769. Long before neural networks were even a blip on the radar, people were trying to physically recreate the human vocal tract. Von Kempelen literally built a bellows to simulate lungs, a reed for vocal folds, and used flexible leather for the vocal tract. And the whole shebang was operated by hand. It's a fascinating reminder that our obsession with making machines speak is anything but new. Today, we've just swapped out the wood and leather for deep learning algorithms and massive data sets. Maya Angelou once said, "Words mean more than what is set down on paper. It takes the human voice to infuse them with shades of deeper meaning." And that beautifully frames our core problem today, right? How do we get a machine to not just spit out robotic words, but actually capture the deep emotional meaning of a personalized human voice? Earlier systems sounded like robots because they basically just stitched pre-recorded sounds together without any acoustic fingerprint. Synthesizing a specific speaker's identity, their true essence, is an entirely different mountain to climb. To understand how we climb that mountain, here's our roadmap. We'll cover 1. From bellows to zero-shot. 2. The audio tokenizer. 3. The quantization codebook. 4. Two-stage voice generation. And finally, 5. Evaluating the illusion. Section 1. From bellows to zero-shot. So here's the absolute game changer. Zero-shot TTS can clone a brand new voice using just a tiny 3-second enrolled recording. I mean, think about that for a second. In the past, if you wanted an AI to sound like a specific person, you had to drag them into a soundproof lab, record literally hundreds of hours of them reading scripts, and then train a custom model solely on that data. But modern zero-shot models like VALL-E, they're pre-trained on tens of thousands of hours of speech from thousands of different people. Because of this massive foundation, when you give it a brand new voice it has never heard before, it only needs 3 seconds to lock onto the speaker's identity, their emotion, and even the room's acoustics. Section 2. The audio tokenizer. Okay, so the encode process acts as our audio tokenizer. It breaks the journey of a sound wave into 3 digestible phases: encoding, quantizing, and decoding. To use a language model on sound, we have to essentially treat sound like text. Language models are built to predict the next word, or token, in a sequence. But a raw audio waveform, it has tens of thousands of data points every single second. It's way too dense. So the encoder squashes this massive wave down into a smaller set of dense vectors. Then the quantizer sorts these vectors into discrete, categorized tokens, basically creating a customized alphabet just for sound. Finally, the decoder's job is to prove this whole thing actually works by taking those discrete tokens and blowing them back up into a fully reconstructed, listenable waveform. Notice how this visually maps the journey from a 24 kilohertz continuous waveform all the way down to 75 hertz discrete embeddings, and then back again. On the far left, you've got our dense input wave, 24,000 real values per second. The purple encoder blocks, using convolutional layers, iteratively step that down. By the time the signal hits the middle quantization stage, we're only dealing with 75 embeddings per second. That is a massive compression, downsampled 320 times. And this middle bottleneck, that's where the magic happens. We've taken a chaotic, continuous acoustic signal and transformed it into a neat, manageable sequence of discrete symbols that our AI can actually read and write. Section 3, the quantization codebook. Now, how do we match a complex sound to a single code? We do it by comparing our encoded 256-dimensional vector to 1,024 possible code words in a codebook to find the closest fit. Imagine walking into a library that has 1,024 very specific colors. When our encoder hands us a new, complex color, we just walk through the library to find the closest match. That library is our codebook. Looking at the flowchart here, the encoded audio vector comes in, we measure its similarity against all the predefined vectors in our book, and we output a simple integer, something like cluster 3. So now, instead of passing around a massive array of decimals, we literally just hand the system the number 3. It's an incredibly efficient way to represent data. But, there's a problem with just using a single codebook. Human speech is incredibly complex.
Trying to capture it with a library of 1,024 sounds is a bit like trying to paint a masterpiece with an 8-pack of crayons. It's just not enough detail. That's why we use residual vector quantization. This layers 8 discrete codes to capture the perfect acoustic fingerprint by recursively quantizing the leftover error. See, after we pick the best match from the first codebook, there's a rounding error, a slight difference between the original sound and our matched code. We take that leftover error, that residual, and pass it to a second codebook. Then we take the error from that and pass it to a third, cascading all the way down through 8 layered codebooks. The first code gives us the broad strokes, and the subsequent codes dial in all those microscopic acoustic details.
Now, to make sure this tokenizer actually works in practice, it's trained end-to-end using 3 specific mathematical loss functions. Because, let's face it, it's not enough to just chop up audio. The system has to learn how to do it without destroying the quality. First up, we use reconstruction loss. This mathematically measures the difference between the original audio and the output audio to ensure they match up. Second, we use an adverse serial loss. This sets up again, pitting our system against a discriminator network whose only job is to spot fake, synthesized audio. The tokenizer has to get good enough to fool it. Finally, the quantizer loss ensures our codebook is constantly updating and learning the absolute best representations of sound during training. This combo guarantees our discrete audio tokens are of the highest possible fidelity. Section 4. Two-stage voice generation. All right, so with our audio dictionary built, VALL-E takes those discrete audio codes and treats them like a language modeling task. It combines text tokens with our 3-second audio prompt. Take a look at the architecture here. On the left, you've got the text you actually want the AI to say, which gets turned into standard text tokens. Down on the bottom, you have the 3-second enrolled recording of your target speaker. That gets pushed through the audio codec we just learned about to create audio tokens. VALL-E takes both of these sequences, looks at the text, looks at the reference voice, and uses a language model to predict the next audio tokens. The goal? To perfectly align with the text but sound exactly like the reference speaker. But here is a crucial detail. This whole thing happens in 2 distinct stages. An autoregressive model sketches the broad strokes left to right, and then a non-autoregressive model fills in the fine residual details all at once. Because we have 8 layers of codes from our residual vector quantizer, trying to generate them all at once would just be complete chaos. So VALL-E splits the job up. The autoregressive, or AR stage, acts like a traditional language model. It generates the very first, most important acoustic code, frame by frame, from left to right. Once that foundational timeline is built, the non-autoregressive, or NAR models, take over. Since the timeline is already established, these NAR models can just fill in the remaining 7 layers of residual codes for the entire sequence simultaneously. It makes the system lightning fast without sacrificing any of that rich acoustic detail. This is where it gets really elegant. Look closely at these exact attention matrices. The green grid at the bottom, that's the autoregressive transformer. The grayed out squares show the attention mask. It is strictly forbidden from looking ahead into the future. It has to predict the next sound based only on what has already been said. But look at the blue grid on top for the non-autoregressive transformer. It's completely open. Because the foundational sequence is already there, it can look at the past, present, and future tokens all at once to perfectly harmonize the residual acoustics across the whole sentence. Bringing it all together, here is the complete pipeline when you actually use VALL-E at inference time. You hand it your text. You hand it your 3-second recording. The system tokenizes both. The autoregressive transformer chugs along, predicting that first layer of sound. Then those results are passed up to the non-autoregressive transformer, which does 7 rapid passes to add in all the depth, the emotion, and the environmental acoustics. Finally, that complete matrix of generated codes is handed back to our off-the-shelf audio codec decoder, and out pops a highly realistic, incredibly personalized audio waveform.
Section 5. Evaluating the illusion.
Ultimately, how do we know if this works? The ultimate judge of this synthesized speech is the mean opinion score. We rely on human listeners to rate the utterances on a scale from 1 to 5. You just can't completely automate the evaluation of art. And speech, with all its nuance, really is a form of art. So we bring in human listeners. We play them the generated audio. If it sounds robotic or glitchy, they score it a 1. If it's indistinguishable from a real human, it gets a 5. When researchers want to prove a specific tweak made VALL-E better, they use a comparative MOS, or CMOS, where listeners hear 2 outputs side by side and simply pick their favorite. Which leaves us with this final, lingering thought. Has this incredible zero-shot technology actually captured the deep meaning of the human voice, or is it just the ultimate 21st century illusion? We started this explainer with von Kempelen's Mechanical Turk. which, fun fact, turned out to be a hoax with an actual human hidden inside. Today, there's no human inside the box. VALL-E uses vast amounts of data and elegant, discrete tokenization to learn the underlying patterns of human emotion and identity. But is it truly understanding the meaning behind the words, or is it just incredibly, frighteningly good at statistically mimicking the sound of meaning, all based on a 3-second prompt? It's a fascinating question to ponder as we watch these models rapidly erase the boundary between human and machine speech. Thanks for joining me for this explainer, and keep your ears open because the future of audio is already here.